Our next unit of study is going to focus on a quantity called momentum, and in this first lesson we're going to look at how momentum is related to force and also the conservation law associated with momentum. So to start off with, we'll just look at the equation for momentum. It's a pretty simple one. It's just the mass of an object multiplied by its velocity. So nice and easy, nothing squared, everything's proportional, right? We abbreviate momentum with a P. Why, I'm not exactly sure. I've read it could have come from the Latin form of impetus, impetere, or something like that, but anyway, we use P because m is already taken for mass, so another reason. So P equals mv is our equation for momentum. And we're going to relate momentum or compare it to kinetic energy pretty often because obviously they have a lot of similarities. They're both quantities that deal with mass and velocity. So you might ask yourself, why do we need two different things? I've got 1/2 mv squared. Why do I need m times v? And the answer is they have different important properties that are both useful. I mean, you could just come up with some other quantity, let's call it, I don't know, z, and say that it's 1/3 m cubed v or something like that. Well, I mean, somebody came up with these ideas at some point, but the reason why they endured is because they had very useful properties. If you could find some useful properties for this quantity here, then everybody would adopt it and they could name it after you or something. But as far as we know, that has no interesting properties, so we'll get rid of it. These guys, on the other hand, have some very interesting properties. We've already seen kinetic energy. It's useful in looking at global energy transfers and figuring out how fast things can go. Momentum, on the other hand, has a couple of distinctions. For one, it's a vector quantity, so put our little vector symbols. The momentum vector always points in the direction of the velocity vector, and so that distinguishes it from kinetic energy, which is a scalar quantity, and we'll get into some details of that more later. The other thing with momentum is that it's conserved all by itself. We have the law of conservation of momentum. We don't have a law of conservation of kinetic energy, right? We have conservation of energy, but we can lose kinetic energy. We can't lose momentum, so it's conserved all by itself. Momentum also is related to forces. So if I have P equals mv, and if I want my momentum to change, the momentum of an object to change, we're going to define that as delta P, and typically we're going to take mass to be constant. It isn't always, like in rocket science, you have changing mass as you're burning your fuel, but we're not quite ready for rocket science. So typically we have delta P is changing because the velocity is changing. Now if I look at this equation here, if I multiply this side by t over t, so I'm just multiplying by 1, I don't have to do it over there, right? Well, delta v over t is acceleration, so we get mat here, and mass times acceleration is the net force. So here is another way of finding your change in momentum. It's the force multiplied by the time over which that force was acting. And you might remember when we were looking at work, we had a similar equation where we had work was the force times the distance instead of the time. So again, we've got some related quantities, but momentum has some distinct properties that allows us to solve some problems that we couldn't solve just with energy considerations. Alright, so let's look at the law of conservation of energy now, and I'll show you some examples of using that other equation later. So conservation of momentum, did I say energy? I meant momentum. Conservation of P, yes, that's right. So just like conservation of energy, this says that you cannot create or destroy momentum. So we can say the initial momentum of an isolated system is equal to the final momentum of an isolated system. Now, an object can gain and lose momentum, but that means that the other objects that it's interacting with are either losing or gaining the momentum that the other object gained or lost. So if we have a couple of objects interacting, often we write this as m1 v1, so the momentum of one object. Actually, let me write it out in terms of momentum first. So if we have one object, its initial momentum plus the initial momentum of another object has to equal the final momentum. And rather than having a whole bunch of subscripts, what your text does is it uses this prime notation, which is not the derivative at all. It's just saying initial and final. The primes indicate the final states. So all we're saying here is that the combined momentum of two objects equals their combined momentum later on, even if they transferred from one object to another. Okay, and then we can plug in mv for each of these p's. So m1 v1 plus m2 v2 equals m1 v1 prime. My one there is a little prime looking. All right, plus m2 v2 prime. Again, we're assuming the masses are constant and you have some initial and final velocities applying to both objects. So there's basically two strategies for solving problems: using conservation of momentum, this equation here, and using change in momentum equals force times time. Okay, and this force is the net force. I'm not always going to write it though. And change in momentum is also m delta v. So a lot of times it's better just to jump directly to this equation here. So two approaches, just like before we looked at work as an approach to solving conservation of energy problems, and then we had conservation of energy equation written similar to this, where you have initial and final. Alright, a couple of examples here. Let's start out with our good old 20 kilogram box. And let's say that there is a net force of 100 newtons to the right that acts on the box for 5 seconds, and the initial velocity, let's say, is 0, and we want to find the final velocity of the box after 5 seconds. Now obviously we could use F equals ma and find acceleration and use kinematics, but we're learning about momentum, so let's try our momentum equation. So the first thing when we have a momentum problem is to ask ourselves, well, am I going to use this conservation of momentum equation, or am I going to use force times time equation? Well, I've got forces involved here, so we're going to use the force times time equation. And so we've got Ft equals m delta v. I just switched sides of how I had it written on the previous slide. So we've got our force here is 100, our time is 5 seconds, the mass of our box is 20, and then we can solve for delta V. So delta V is going to be 500 over 20. Okay, so we get 25 meters per second. Now I want to find the final velocity, and we need to be careful. This is change in velocity. So this is final minus initial equals 25 meters per second. Because the initial velocity is 0, then yes, we can say the final velocity is 25 meters per second. But if the initial velocity were not 0, this would be my change in velocity. Alright, so there's one example there. Let me get a new slide here. Duplicate, erase. Alright. Sorry, I didn't have enough slides ready. Erase, 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 erase. Almost done. You guys don't have anything better to do than watch me erase stuff, right? Okay. Alright, one more quick example. Let's say we have two stick people. This stick person has a mass of 50 kilograms. And they throw a heavy ball, like a medicine ball, with a mass of 10 kilograms with a velocity of 5 meters per second. And there's another stick person over here, a little bit smaller than that stick person. We'll say their mass is 30 kilograms. And this person was at rest initially before they threw the ball. Let's also, we have these two stick people, and let's say that they are standing on a frictionless surface. They're out on some lake with absolutely no friction whatsoever. So I want to find out how fast is this person going after they throw the ball, and then how fast, let's say their initial velocity is also 0, how fast are they going after they catch the ball? And we can use conservation of momentum for this. So first, the fact that there's a stick person over here catching the ball doesn't affect what goes on with this guy and the ball. So we can use m1 v1 equals m2 v2 because we have mass and velocity information instead of force and time information. So plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Now before, this is my initial side here and this is my final. So we want to take the initial as before this guy threw the ball at all, which means that neither this person is moving nor the ball. So all of this stuff over here is 0. This entire side is 0. So we have m1 v1 prime equals negative m2 v2 prime. Alright, so if we start plugging in our numbers here, I'm going to call the guy 1 and the ball 2. So the guy has a mass of 50. v1 prime is his final velocity, that's what we're trying to find. The ball has a mass of 10, and I've got a negative sign here. That just tells us that the person is going to go backwards and the ball is going to go forward. They're going to be in opposite directions. Negative 10 times 5, so that's going to be 50 divided by 50, and we're going to get v1 of negative 1 meter per second. Alright, so so the negative tells us that the person is going backwards because we plugged in a positive for the ball's velocity, so the other direction's got to be negative. Now if we look at this guy here catching a ball of that mass with that velocity, we can do another m1 v1 plus m2 v2 equals m1 v1 prime plus, run out of room here, m2 v2 prime. Okay, I think I got an extra prime on my m there we need to get rid of. Alright, so if I plug in, we'll still call the ball 2 and the person 1. So the initial velocity of the person is 0, so this term goes to 0, but here the initial velocity of the ball is not 0. We're saying the initial is while the ball is in the air flying at this person, and the final is after he caught the ball. So m2 is going to be 10, and v2 is going to be 5. Okay, now on this side, you could leave it separate like this, but if the person catches the ball and starts sliding backwards because they're on a frictionless surface, then the ball and the person are going to have the same final velocity. So I'm going to say m1 plus m2, just treat them like one object where their total mass is the combination of their masses. And then we can just call this v prime. It's the one final velocity that there is. I don't need to distinguish between two velocities because there's only one. Alright, so I've got 50 over here, 30 kilograms and 10 kilograms. I'm going to have 40 here times v prime. So v prime is going to be 50 over 40, which is 5/4 or 1.25 meters per second, which we would expect this person to be going faster than this person, right? Because they were lighter, and essentially the two were interacting through the intermediary of this ball here. Alright, so two different approaches to solving problems. Pretty straightforward stuff. Either use conservation of momentum or use force times time. See you next time. Bye.